Hello, my geeslings. I'm with geesling number one pins right now as I sit here recording the introduction to episode 36. At least I believe it's 36, with my friend and teacher, Justin Clarke-Doane. This is the third episode we've done. I think he was on episode 7, and also another episode with David Albert, both of which were great because Justin's extremely knowledgeable, and the fluidity with which he talks about all sorts of really complicated philosophical questions is mind-blowing to me. And every time I talk to him, I just think, well, shit, I'm never gonna be able to do this. But anyway, it's really inspiring for me to talk to him, and also I always learn a ton. In this episode, we talked pretty much exclusively about the philosophy of math, and in particular, how to answer the question, what is mathematics? Because it's a very big, loaded question, and there are lots of different ways that it can be answered. In particular, I think the episode was really geared toward or around a course that he just taught at Columbia University with Chaim Gafman, another Robinson's podcast veteran. He's been on episode 1, 11, 21, and 31 thus far. So Chaim is a mathematician, a philosopher, a probability theorist, and you'll hear a bit about how he answers the question, what is mathematics? But we also did an episode exclusively on what is mathematics. I'm not sure at the moment if it is episode 11 or 21, so I'm going to very quickly figure that out right now. It is episode 21, what is mathematics? So if you want to hear from Chaim himself, just listen to episode 21. But anyway, so Justin and I talk about what is mathematics. And some of the questions in particular, or the more particular questions we get into, are whether or not ancient and contemporary mathematics are the same subject, what the point is of mathematical proof. We talk about the four-color problem and whether or not humans will eventually be replaced by artificially intelligent mathematicians. We talk about skepticism and classical logic. We talk about whether or not mathematics has the capacity to explain. And explanation is itself a topic in philosophy that I don't really know that much about. We talk about calculus and why it was important to rigorize it as opposed to just leaving it somewhat intuitively defined or developed as it was done by Newton and Leibniz. Then we also talk about mathematical knowledge, and in particular, the Benacerraf-Field problem. And then we finish by talking about Zeno's paradoxes, which I have a great love for. And I also just lied because that's not what we finish with. We actually finish with 5 minutes or so on Indian metaphysics or Indian philosophy more generally, because unbeknownst to me, that was what got Justin into philosophy in the first place, or at least it was his first interest and still informs his views. But unfortunately, we don't get to go into much depth there because I had already kept Justin for about 2 hours and he had to go. But I think in future conversations, it's something we're going to discuss much more deeply. Anyway, as you can tell probably from this introduction, it was a very intense episode, another great one. I'm so grateful to Justin for really humoring me and being part of this, but he seems to enjoy having the conversation, so all the better. Anyway, I hope you enjoy the conversation as much as I did and he purportedly did, and as much as Pins enjoyed sitting in my lap for most of it, and I will leave it at that. So last time we were together, or last time we did a podcast, it was with David Albert. And I tried to start off by talking about ice cream, but I think he wanted to just get straight down to physics, which is okay. But have you eaten any interesting ice cream lately at all?
Not interesting. Have eaten a lot of ice cream. Last night I had a bunch of what's the one with the 3 different colors, and then I put chocolate chips on it.
Neapolitan.
Yeah. So I ate a large quantity of one of the the things of that.
Okay.
Just
What
for health.
brand?
What?
What brand?
Gosh, it's like, what's like the main brand? It's like
Edie's, Dryer, Briars.
Edie's.
Edie's.
Yeah.
Okay,
Edie's.
Edie's is pretty good. But
Yeah.
so last time I think we talked about Bluebell a bit, but have you heard of Salt and Straw?
I don't think so.
So Salt and Straw is Portland based, but I think they've got sort of the gourmet ice cream down pat. Like they make some of the best ice creams, and they have all sorts of crazy flavors. And there's one right by me in Stanford, so they have specialty flavors every month. And in the past, like 2 weeks, I've had a pear and blue cheese flavored ice cream. And do you like blue cheese?
No, I don't. I don't.
No,
I don't think so.
I really don't either. So
Yeah,
I didn't particularly like that one. But then there was a roasted turkey and cranberry sauce ice cream, and that one was I think they wrote about it in the Wall Street Journal, but it was actually a phenomenal ice cream. I was apprehensive. You can see it, yeah. I was apprehensive at first because I thought it was going to be like pulled turkey breast or something, but it was actually turkey bacon. And I don't know if you've had like those bacon chocolate bars, but they're pretty good.
Okay. No.
Okay.
I haven't. Yeah.
Okay, and then the last one I wanted to tell you about for show and tell was I had one today. It was from Halloween, but it was called Creepy Crawly Critters, and it had chocolate covered crickets and toasted mealworms in it.
You mean like real ones?
Yeah, like real ones.
Oh.
I know.
Okay.
I was feeling really brave for that one.
Yeah, that's impressive. I don't know if I would be up for that, but that's okay. That's amazing.
Okay. Thank you for listening to my show and tell.
Thank you.
But now for more philosophical things.
Right.
So Chaim and I already did a podcast on what is mathematics, which is sort of what I hoped you and I would talk about. And the way he answers this question, which you know, is somewhat like the following. It's mathematics is what mathematicians do. And that doesn't seem particularly illuminating, but when you get like deeper into it, it's kind of, it can be sociologically or historically interesting because it it allows for hypotheses or theses like the one he has that there's no phlogiston. I always pronounce it wrong. I want to say phlogiston, but I know it's phlogiston. There's no phlogiston in mathematics, and it's the only science, natural science, without full-scale revolutions. But I think you view, and I see this as a problematic account of what mathematics is, because it doesn't seem to answer certain questions that we find really important. But just right off the bat, do you think of historical mathematics as being fundamentally the same discipline as what's being done today? Because if that's not the case, then there's already a problem with the thesis.
Yeah, I mean, so there's a sense in which I'm not sure I disagree with him, believe it or not, about or what you're attributing to him. I disagree with some of it, but I'm not sure. So on the question of, first of all, like whether math today or starting in the 19th century, sort of its axiomization and the kind of approach to proof and standards of rigor that were established in the 20th century, whether that's the same discipline as, for example, the Greeks, much less, the Babylonians or the Islamic world in the Middle Ages, or the Mayans, or the Egyptians, or indeed medieval Europe. Um, that strikes me as, a question of just how to kind of use the word. So I don't think there's some deep question in the vicinity of is what, it is what Euclid was doing the same thing as what uh, uh, you know, Bill Thurston was doing. I don't think there's a deep question there. Under some interpretations of the term mathematics, sure, it will turn out that we were doing the same thing. Under others, it won't. And the more it seems to me productive discussion is just to be explicit about what are the similarities and differences between what some people call math, or what is typically called math, and say a history of math book,
Mm-hmm.
in different periods, and what we call math today. And there are striking differences. There are differences, in that for most of recorded history, proof was not central to math in the sense that
Mm-hmm.
we think of proof today.
Right. You
When
mentioned that like Chinese, I think some Chinese mathematics textbook, they'll just give problems and solutions, and they don't even really consider giving anything like a proof. Maybe there's like a
well,
little justification.
right, there's a sort of algorithm, and there's some discussion, some commentary on the algorithm. But the math was very advanced, so it's not a question of advanced or not. It's a question of priorities. Do you care about proof or not? And I think it's an interesting question why the Greeks decided to care about proof, and why we decided to follow them. After the Renaissance, to pick up that strand. But even if you just look at the part of history that you might call like the Greek tradition of math that we're part of, where proof takes a central place, that's a very hodgepodge history. It's not at all. I mean, I don't think it's helpful to just label it all math. It's like, sure, it's all fine, call it all math, I don't care. But there's dramatic differences in standards of rigor, in the conceptions of what you're talking about. Are you talking about literal constructions on
Mm-hmm.
with compass, or are you talking about abstract objects? And if you're talking about abstract objects, what are their nature? For example, what would the numbers be? And of course, the Greeks famously had heretical views about this, given their worries about incommensurability and stuff. So, is geometry and arithmetic, are they somehow the same subject in two different guises or not? All these sorts of things. So on the question of are all the different things we call math in a history of math book really math? I think that's just a question of how to talk. There are dramatic differences, though, however you talk, and it's useful to study those. Sorry.
So yeah, Heim, I I feel like I'm quoting him. I don't want this to be like I'm a Heim surrogate, and then you're having to
Yeah.
like put down the straw man that I embody. But he
No.
likes to say that mathematics is the art of tinkering. That's one thing that he says. And that what mathematics is, other than it being what mathematicians do, is that it's about organizing information.
Mm-hmm.
And so he will say, I think he would disagree with you and say, no, there is something fundamentally similar and important uh, to what the Egyptians did, what the Greeks did, and what we do today. And it's we're organizing information in some sort of way. And that's what makes them all mathematics.
Yeah, I mean, my worry with that is not that it's false as a necessary condition. It's that it's so general and vague that it's hard for me to see how that could distinguish math from any subject. I mean,
Mm-hmm.
what intellectual subject doesn't involve organizing information and tinkering theories?
Mm-hmm.
Um, so So I would just need to hear a lot more detail and much more meat on the bone to see how that sort of says anything controversial.
And so some of the ways in which they differ that you think are really important are, this was an example you used, that Eudoxus's proportions might not be what we had in mind when we're talking about the real numbers, or uh, when they used protractors and rulers 2,000 years ago, whereas now we're using not that, but we're using automated theorem provers and complex models. And I mean, they didn't use proof. I mean, that's obviously a blanket statement. In the elements, they obviously, Euclid obviously used proof, but there were, like, those Chinese mathematicians we talked about weren't using proof, but now proof is central to mathematics. So there are some things that we certainly say it's not mathematics today if you don't have these things, but they didn't have them back then, so they're not doing our mathematics, at least.
Yeah, well, I mean, just to be clear, like, proof is obviously central to the elements, and that's why, it's been used for 2,000 years as some kind of paradigm. But what counts as proof in the elements is not what counts as proof today. I mean, take the very first proposition about, constructing an equilateral triangle. That just has a obvious hole in it from the standpoint of today, which is that the circles used to construct it intersect. That would not be okay today. You can't just take that for granted. It's clearly relying on intuition or the diagram or something. So, but right, in other traditions, you don't even have something that bears a family resemblance to proof today, and it seems clear that the explanation for that isn't that somehow, like, they weren't capable of coming up with proofs. It's that it's a good question, I think, to ask why we want proof.
Mm-hmm.
Why don't you just want truth? Why don't you just want to know what's the case? Why do you want to put it in this sort of recondite language, in this premise conclusion form that's hard to read, that starts from highly abstract principles that most people will never acquaint themselves with? I mean, I think that's a good question. I'm not saying
Yeah.
that rhetorically because I think it shouldn't be done, but anyway. So yeah, just to be clear, the Greeks, unlike the Indians or the Chinese, did use something that we think of as proof, but it's not the same standard of rigor.
Hmm.
Yeah.
So, I mean, you've brought up and Broughton. I feel like my dad used to correct me when I was a little kid. I would always say Broughton, but okay,
You can say it here.
you've brought up uh,
Yeah.
a good question, which is, I mean, what's the point of proof? Why proof? Was it the same then as it is now? And I you've given me a couple of competing answers, and one is a proof is an argument that generates insight and understanding. And do you think that holds generally, or there are problems with that? I know I'm setting you up to
Right.
maybe go into the four color theorem a bit at some point
Well, no. So I mean, right. So I think,
down the line.
yeah. So I think that, yeah, in the class, I just pointed out that there have been two kind of ideas of proof, or idealizations of the notion of proof, that historians have distinguished. One is associated with, like, Aristotle and Leibniz, and that has to do with kind of certifying an argument. Like, so on this conception, a proof is something that sort of guarantees the validity of the argument. It doesn't guarantee the truth of the premises, of course, the truth of the axioms, but guarantees. On the other conception, though, truth is more like what you get out of, like, Plato's Meno, where the slave boy comes to see that. I guess what is the example? I guess he sees the length of the hypotenuse, or so I can't remember whether it's the Pythagorean theorem that's used, or something else. But anyway, the argument is a kind of aha argument. It's like, oh, that has to be the answer. and you can see why. And the official reasoning in Plato's Meno, like any other of his dialogues, is that it's a back and forth between two individuals, a sort of like, here's a hypothesis, here's why that doesn't work, here's another hypothesis, and that's not a proof in the first sense. It's not like a sequence of symbols, each one of which is a premise or follows from the previous line by a rule of formal inference, the last line of which is the conclusion. But it generates insight and understanding. So you have these two different, I think, conceptions. So that's kind of associated with, I don't know, Plato and then maybe Descartes. And it seems to me like part of what explains sociological differences in contemporary academic, I'll call it math, but it cross-cuts, disciplines, in the sense that some of these people are in philosophy departments, some of them are in computer science departments, some of them are in math departments. Contemporary math is what's kind of more important, or what should we be after, the Platonic proof or the Leibnizian proof? And of course, ideally you want both. And so you might want a Platonic proof, but then you want it backed up by a Leibnizian proof. And that's the idea that's exactly the idea that here's what we mean by rigor. If you prove something in the Platonic sense, there should be a Leibnizian proof backing it up, such that the premises are something like the ZFC axioms, and the argument can be completely carried out by a checked by a computer as first order valid. But that's sort of an article of faith that all Platonic proofs could in principle be done that way. That is, all the proofs that count as, proofs in informal standard mathematics that people find illuminating and persuasive could in principle be there's a surrogate proof in, say, first order ZFC that's mechanically checkable, that's like an Aristotelian Leibnizian proof. So the original question was, do I think all proofs are like that? That they generate insight and understanding? Certainly not all the things that, get called proofs, including, for example, proofs that involve computers, like the four-color theorem, are like that. But it does seem to me like most of sort of, core or prestige math, those are the kinds of arguments people like. People want intuitive, illuminating arguments, and the more technical and kind of Leibnizian, the less actually kind of impressive and enjoyable the mathematics,
Right, but there's an analog to the really brute force, complicated, not surveyable proofs like those done from axioms by a computer in the core of mathematics that's being done today, in that most of those proofs aren't perfectly rigorous, and then once you rigorize them, a mathematician can't read them because because nobody ever does them, but because they would be essentially impenetrable and thousands of lines long for something very simple.
Right. So maybe we should just, for purposes of people watching, distinguish two notions of rigor. So I was talking about standards of rigor and stuff, and the arguments are, in an ordinary math journal, as far as I know, are perfectly rigorous generally by the standards of the mathematical practice, the mathematical community. They're not rigorous in another sense, which we have yet to distinguish, but I gestured at, which is they're not first order valid. And that is the notion that mathematical logicians study. It's the notion that every philosophy student learns when they take logic. It's the notion of valid that can be checked by a machine. And you're absolutely right. So what I was saying was, ideally we, the sort of philosophy, computer science types want it to be the case that the final arbiter of validity is something you could check with a machine. So that means that every argument in a mathematics journal must have a surrogate that's mechanically checkable. But the mechanically checkable arguments are not things anyone can comprehend. As you say, they'd have way too many lines, and they just look like incomprehensible computer code, and certainly are not Meno type proofs, So in that sense, underlying every argument in a math journal, if you think the final arbiter is formal rigor, like rigor in the sense of first order formal provability, in that sense, every mathematical argument is backed up by something that's not amino proof.
Mm-hmm.
And there's interesting kind of epistemological questions of epistemological priority when you realize that. Like, why do we think that provability in first order ZFC is the final arbiter? And if anything, it seems like the arguments that will back that up will be informal amino arguments.
Mm-hmm.
It's not like because a computer told us so. So, sorry, that's my phone. So sorry. The original thread was that I guess you're just saying that the things that fill up journals, those generate insight and understanding. But if someone were to show that there's no surrogate in first order ZFC that's formally valid, that would invalidate the proof. And in fact, that's exactly what here. I mean, here's a very concrete case to illustrate that for the skeptics. Think about the proofs of the independence of the continuum hypothesis by Goodall and Cohen. Those concern formal provability. Those concern, like, in order to talk about provability, you have to talk about an idealized object, idealized proofs, and idealized systems that people use. Finite, proofs, finite string symbols. Yeah.
Well, maybe before we talk about this, you could just briefly say what the continuum hypothesis is. And
sorry. Yeah. Sure. So the continuum hypothesis says that there's a bijection between every uncountable subset of the real numbers and all of them, or assuming what's typical, but by no means everyone who thinks about this stuff agrees, what's called the axiom of choice. It says the size of the real numbers, the cardinality of the real numbers, is the next greatest after the size of the natural numbers.
Okay, so now channeling David, can you say that in normal guy English?
Oh, well, yeah. So assuming the axiom of choice, which doesn't matter right now, it's just an axiom that was controversial at the turn of the 20th century, but now only kind of people who worry about foundations think very much about it. Famously, Cantor showed that in a reasonable sense of size, you can have different sizes of infinity. Mm-hmm. So this is surprising because, for example, you can pair the even numbers with the natural numbers. It turns out that you can pair the rational numbers with the natural numbers. You might just think infinity is never ending and they're all the same. They all bleed into this. Any infinite set is just the same. And Cantor showed that that's actually not true. And there's this very simple and beautiful argument known as the diagonal argument, showing that the set of the real numbers, which includes irrational numbers that can't be written as fractions of integers, like root 2 or pi, that set is, in a well-defined sense, bigger than these other sets. And the well-defined sense is you can't do that pairing. You can't do a bijection, a one-to-one pairing, so that all the numbers are used up and get unique partners in both sets. And here's the next question. How much bigger, if they're bigger, is the set of real numbers and the set of natural numbers? Assuming the axiom of choice, the continuum hypothesis says that it's the next size up. The real number, the set of real numbers is the next size up from the set of the natural numbers. But in the 30s or 40s and then the 60s, it was shown that from standard axioms, and in fact, any axioms known as large cardinal axioms, which have been seriously considered, if those axioms are consistent, then so is both the continuum hypothesis tacked onto those axioms, and so is the negation of the continuum hypothesis tacked onto those axioms. Meaning that from the standard axioms, if they're consistent, you can't prove or refute the continuum hypothesis. And as I say again, not just standard axioms, actually, something quite a bit stronger than standard axioms. Um, uh, so so the point is that the proof of that, in order to be able to prove something about provability and what you can establish or not, you have to idealize and you have to work with a formal notion of provability.
Mm-hmm.
So what's really shown is there's no formal proof in the formal system of ZFC, Zermelo-Fraenkel set theory with the axiom of choice plus large cardinal axioms of the continuum hypothesis, a formal statement of the continuum hypothesis or its negation. Now here's the point.
Mm-hmm.
When that was done, everyone took that to show, okay, well, I won't waste my time trying to prove the continuum hypothesis or its negation.
Right.
Informally prove it. That is,
Right.
prove it in the ordinary sense of proof that mathematicians follow.
So
evidently,
mathematicians really trust the formal
it would
mathematical logic.
seem that, it would seem that despite whatever rhetoric you might have, like, that you might hear that formal provability is ugly and has nothing to do with understanding and stuff, that might all be true, but it does seem like the buck stops there. If someone shows there is no formal proof in, say, first order ZFC plus large cardinal axioms of the continuum hypothesis or its negation, if the axioms are consistent, then nobody's going to be looking for a proof in the ordinary sense of proof of that hypothesis. They will look for new axioms, for example, but that's not going to be an ordinary mathematical activity. That'll be, philosophy.
Yeah, I would ask you about the search for new axioms, but I feel like that would take us pretty far afield from what is mathematics at the moment. Even though I'm curious about your thoughts on that, but this might be a good time to, unless I'm making you talk too much with explication of things, but this might be a good time to go into the four color problem, and then more importantly, the four color theorem. And I mean, there are a couple of interesting things about it. I mean, one, I know you like talking about or thinking about the role of computers in mathematics and whether or not they'll replace mathematicians, which I did talk to Michael Harris about on the show a while ago.
Oh yeah, what do you have to say about that?
I think he said that. Well, we can talk more about that once we talk about the four color problem. But he talked about mathematics being a human activity of understanding that's not going anywhere. But then it also just raises questions about again surveyability in a similar sense to the formal analog. But so what was the four color problem? Because I think it had been around for a very long time, right? It wasn't a new problem when it was solved.
So
I can look that up actually.
So I think it had been around something like 150 years. The four color theorem is actually not something that I've thought much about, but it's that every planar map is four colorable. What I think is the standard statement of the theorem.
I can read the standard statement.
Yeah. Okay.
The four color theorem states that no more than four colors are required to color the regions of any map, so that no two adjacent regions have the same color. So that's the theorem, and the problem is whether or not that was the case, whether or not you needed four colors, or whether you could do it with four colors.
Right, and where adjacent doesn't just mean touching at a point; it means like having like a border. Yeah. So I actually don't know the detailed history of this, but I think you're right that I think it had been around for at least 100 and maybe 50 years or something when the
1852. So you're right on the money.
Close. Well, I think the proof though was in the set in the 70s, so I'm not quite.
Yeah, it was 76.
Okay. So again, you should talk to historians about this. But right. So there's this proof that involves a significant step where a computer checks a zillion cases, and also according to the architects of the proof, my understanding is kind of does more than that and starts strategizing. And that part of the proof is not surveyable by a human being. There's been enough checking of the argument, my understanding is, there's been enough checking of the argument that no one is in doubt that it's valid at this point. In fact, if anything, it's probably been checked much more carefully and closely than most arguments in math that are interesting. But, some people went so far in the 70s, at least, and maybe later, to say that's not a proof. I don't know what nonverbal issue could be at stake there. The important thing that we can all agree to is that there's something that people didn't like about it. So you can just distinguish two questions. One is like, does the conclusion follow from the premises? And it really does seem to me like, unless you just have skepticism about classical logic or something, which is another discussion and an interesting one, yes, we have excellent reason to think so. Another question is that the kind of thing we should be striving for in math? Just figuring out what follows from what? I mean, suppose that now we have automated theorem provers, proof checkers, proof assistants. You don't just want a bunch of phone books of, if the axioms, then this, or if the finite subset of axioms needed in the proof, then this. And here's another one. And that one looks interesting. Okay, so we put that in the interesting box, but you don't understand why any of it's true. I think this is the kind of, presumably, though I don't know. I take it that's kind of what Michael Harris is getting at.
Exactly.
That why do math? It's not to accumulate stacks of validities. It's to understand stuff, and it's to understand relations between ideas or something. I mean, again, that would be a very general conception that wouldn't distinguish math from a lot of things either. But and the four-color theorem has been frustrating in that, as far as I know, but again, you should ask a historian, there doesn't seem to be any prospect of coming up with a purely surveyable proof, a proof that doesn't involve, checking zillions of cases and some other slightly fancier things on the part of a computer. But I'm not an expert on this topic.
Okay. Something that you said 2 minutes ago that had me curious is that there are reasons for being skeptical about classical logic.
Mm-hmm.
And I'm wondering what the reasons are that you have in mind.
Yeah, so I mean, to me, the most important question in the philosophy of logic is what is at stake? What is the dispute when people dispute whether classical logic, for example, is correct? I'm going to bracket that for a second and pretend that that's a clear question, or sorry, that has it's clear what's at stake. We can talk about what might be in a minute, but assuming you know what it means to disagree with classical logic or something, I mean, there's lots of different kinds of reasons. So,
right, like the law of the excluded middle or something.
So right,
so
intuitionists have objections based on constructive concerns about the constructivity of or constructibility of examples. A more radical concern is, one stemming from paraconsistent logics, where you don't even accept things like disjunctive syllogism. That's the inference rule that says that if you know that P or Q and you know that not Q, then you can infer that P. And paraconsistent logics, for those who haven't heard that term, is just they're logics where it's logically possible that something is both true and false, or a contradiction holds P and not P. That doesn't mean that something is both true and false. That's not part of paraconsistent logic. Logic doesn't tell you what's actually the case. It just tells you what's possible and has to be the case as a matter of logic alone. And what it's saying is that you can't rule out contradictions as a matter of logic alone. So there are, there's lots of, there have been lots of different logics proposed in some sense of proposed. There's something called quantum logic that von Neumann and Birkhoff, I think, proposed, that gives up on something called the distributive law. they're continuum valued logic. So there's, just as a matter of sociology, there's all these different things that are called logics, and there in some sense is a dispute about which one is the right one among some people. And a good question is what in the hell that means. But pretending for the sake of argument that we know, some of the objections are things like, against law of the excluded middle, against disjunctive syllogism, and so forth. Different rules of inference that are classically valid in ordinary math, but they're not valid in some of these other logics.
Okay, cool. That satiated or satisfied my curiosity. But okay, back to the four-color theorem, or maybe a little bit before the four-color theorem. We talked about the two sort of purposes, maybe, or two purposes of proof. So generating insight and understanding on the one hand, and then on the other, something that conclusively establishes its conclusion. And Ronnie Rachvelpula, your student, gave me a question for you that I don't totally understand because I'm not up on these debates, but it relates to the first branch about generating insight and understanding.
Okay.
And my understanding is that there are currently a lot of debates going on about what explanation is. And Ronnie was wondering how you feel about mathematical explanation in particular. And I'm wondering how a proof relates to that. I mean, in what ways does mathematics explain, or can it be explanatory?
Yeah, good. I mean, so again, like I want to avoid verbal questions about the meaning of the word explanation. There are debates about what counts as an explanation in philosophy of science. Again, I think the most productive way to approach those debates is kind of like, what should it mean? What are we after? Not a question of natural language semantics about how people use the word explanation. Now, our very own colleague, I guess no longer your colleague because you left, but anyway, our colleague Philip Kitcher has a very influential view of explanation, which applies directly to mathematical cases. It wouldn't distinguish between causal cases where you're explaining why the billiard ball went this way rather than that way versus mathematical cases. And it's, probably going to butcher Philip's view here because it's been a while since I've read his stuff on this, but I think basically he regards an explanation as a set of sentences that imply the thing you want explained, that's unifying and simplifying, and there's no reason you can't have that in the mathematical case or the philosophical case or the historical case, or there's nothing special about science, empirical or physical science, and when it comes to that kind of explanation. So if the question is, are there mathematical explanations in a perfectly reasonable sense of explanation that, our colleague has developed, it seems to me, yes. If the question is, are all proofs that are regarded as legitimate explanatory? Well, setting aside cases like non-surveyable cases like the four-color theorem, not, it seems to me, on any ordinary sense of explain, because reductio proofs are okay. Oh
yeah, that's an interesting case. You want to just briefly say what that is?
Yeah.
People
the
don't.
Classic case is the classic case to illustrate a reductio proof is the proof that root 2 is irrational, and that's to say that root 2 can't be written as a fraction of integers where the denominator isn't 0. And the way you argue for that, the famous proof of that is, suppose you can write it that way. And you end up with the result that both P and Q, so suppose that you can write R as P over Q for some integers P and Q isn't 0. What you end up arguing is that if you could do that, and you suppose also that P and Q are in lowest terms, so they have no common divisors other than 1. So the way you argue is, suppose you can do that, well, what you end up with is the conclusion that both P and Q are even. But if they're both even, they're not in lowest terms. So so you end up contradicting.
Because they're both divisible by 2.
What's that? Yeah. So you end up contradicting the assumption that root 2 can be written as P over Q and where those are lowest terms. Now, all that shows you is that some assumption has to be wrong, and the way you set it up is supposed to compel you to say that the assumption that root 2 is irrational is wrong, can be written that way, or sorry, is rational is wrong. But it doesn't, I mean, in an ordinary sense, it seems to me like no one would say that was an explanatory proof. You just know that something went wrong, but you kind of don't know what. So insofar as reductio proofs are legit, at least typically I would think of those as not explanatory in an ordinary sense of explanatory. But again, the word explanation, I don't want to do natural language semantics on explanation. It seems like in different circumstances, you want different things. You want different kinds of insight. And certainly sometimes I think that reductio proofs can be insightful in the requisite way. But no, if the question is anything that's regarded as a proof, setting aside the kind of 4-color non-surveyable cases, explanatory, in an ordinary sense of explanatory, I would say no. I mean, because of reductio proofs, among other things.
Okay, interesting. And then, so the other side of the coin again was that a proof conclusively establishes its conclusion. And this notion somehow hinges on rigor, which you looked askance. I wasn't sure if you were disagreeing with me.
No, I mean, right. There's a sense of corresponding to formal validity, which corresponds to
and this sort of leads me to calculus. And because calculus was first formulated without anything like the rigorous foundations it received in the 19th century.
Mm-hmm.
And I'm wondering if you could say a bit about how calculus came to be in this non-rigorous sense, and then maybe we could talk a bit about Berkeley's criticisms of it, because they're so biting.
Yeah, I mean, again, so I'm no historian, so you should talk to historians if you want something competent on Berkeley and the exchange.
With that caveat.
But before we talk about that, maybe I just want to say, though, something that we didn't get to, which strikes me as very important, which is that the idea that even formal provability corresponds to something like certifiability or guaranteeing the truth, assuming the premises, that strikes me as a fantasy. And this strikes me as exactly one of the places where there's a sort of mythical mathematics, and then there's the math that when you look under the hood philosophically is the real life thing. And unfortunately, the real life thing just doesn't live up to the myth. And the reason is simply that even if you knew that an argument was formally valid, so let's take an argument that's checked by a computer, there's of course two ways that you can worry about that. 3 ways, actually, you can worry about that argument. The first is, of course, you can worry about the axioms. And this is exactly what people did worry about a lot at the turn of the 20th century. Are impredicative axioms okay? Axioms which make crucial, definitions which make crucial reference to the kind of thing to be defined in them. Are uncountable totalities clear in the way that countable totalities are?
Is that an issue of axioms?
Well, I mean, if you have the axiom of infinity, you're assuming the existence of an infinite set, not just infinitely many things. And, you
Hmm.
know, and finitists, not ultra finitists, think that that's not a clear idea. Like a completed infinity is not a clear idea. Once you have the axiom of infinity, then you take the power set and, you'll have uncountable totalities.
Yeah.
Um,
Okay.
but right, like radical predicativists like Weil or Pfefferman, they think the natural number structure is clear, but they think that you know that as soon as you start talking about things like the continuum, that's not clear. So you want to be able to talk about infinitely many things, as in arithmetic, where you quantify over infinitely many things. But it's different to say you can talk about that set and look at that as an object in its own right. And so anyway, the point is, there's one just source of skepticism is, of course, that if there are infinitely many prime numbers, if you prove that validly from, say, the Peano axioms, there's the question of, are the Peano axioms true? You only prove that there are infinitely
Hmm.
many prime numbers if the Peano axioms are true. You might say you at least prove the conditional if insert the finite subset of Peano axioms that you used in the proof, then there are infinitely many prime numbers. Okay, fine. You can do that in any area, though. Like if some theory of astrology is true, let's regiment it, let's axiomatize it. Then you've got bad luck coming or something. So if math
Right.
is actually sticking its
And
neck out and saying anything besides here's what follows from what, then you got to worry about the status of the axioms. But even if you want to say no, math doesn't even need to worry about about the axioms. It's not sticking its neck out. It's just
right.
logic.
So somebody, I'll pretend to be Gödel for a moment. So somebody like Gödel might say that some axioms, like the axiom of pair, for instance, just press themselves upon us as true, and that because of our mathematical intuition, that's sufficient that we can take some axioms as just true, and we don't need to question them any
Right.
further. But then you're saying, okay, we'll grant you that, then we'll move on to the next issue in this
Well,
fantasy.
no, I was saying, suppose that you agree that the objections that I just raised to the
Oh,
idea that math ever certifies the truth of its conclusion, because it never certifies the truth of the axioms beyond reason, beyond all doubt. I mean, there are still debates to this day about the axioms of large cardinals, the axioms of ZFC, including choice, the axioms of foundation, the axioms of replacement, the axioms of power set. And even, I mentioned Peano arithmetic, where you could carry out the proof that there are infinitely many prime numbers. There's a famous book by Edward Nelson that begins, I reject all instances of induction because it's circular. A number is defined as an object satisfying every inductive formula. So
is that the predicative
yeah,
arithmetic
predicative
book?
arithmetic is the book. And now you might say he's an outlier or whatever, but the point is, this is just philosophy. I mean, now we're just having a debate that is never going to be settled once and for all. You can do poll numbers, and you can say that look, Edward Nelson was a heretic, and normal people don't think this, but he probably thought about the issue a lot more than most people who use the Peano axiom. So it's not very satisfying to be like, Timothy Williamson's view about knowledge, has been proved false because 99% of people don't think that E equals K. I mean, okay. But so anyway, one issue is just that if you want some kind of certitude that goes beyond just poll numbers and philosophical agreement among most, then one problem with mathematical proof is that at least to date, we have not gotten that with the axioms. Most people, of course, don't care about the axioms. Most people wouldn't even be able to name what they are. That's not a normal mathematical activity. But among those who do, it's just not true that everybody agrees on the axioms. Okay, but suppose somebody were to say now, okay, but I don't care about the axioms. Give me a break. This is like metaphysics. I'm telling you what follows from the axioms. Well, strictly speaking, first of all, you wouldn't want to do that because claims about what follows from what are really arithmetic claims, specifically claims about what doesn't follow from what are really arithmetic claims. And it's consistent to say false things about that by Gödel's second incompleteness theorem if arithmetic is consistent. So, okay, so let's say what I really mean is they're conditionals. If this, then that. And if you can prove the thing, then that conditional turns out to be a logical truth. Okay. But now we get to the debates about logic. And the fact is, once again, just as a matter of sociology, it's not even true that all parties who think about these things, which of course is a tiny minority of people in the world, there's not,
Right.
no department, even in philosophy, is desperate to hire more people to think about which is the right logic. Those are not, those are, luxury items even in philosophy for a philosophy department. So definitely not in the math.
Columbia wanted you.
What's that?
Well, Columbia wanted you.
Or I forced their hand somehow or something. Yeah, it's not really clear why I'm employed, but here we are. Anyway, so definitely not in a math department. It's going to be very hard to get a job if part of your work is defending intuitionistic logic or something, or a large part of it. So the numbers of people who even are aware of these issues is vanishingly small. But among those who care and know about them, it's just not true there's agreement over what the right logic is, or even what that question means. And so hence what counts is even a conditional we should stand by of the form, if these axioms, then this theorem. Like, if finite subset of Peano axioms, then there are infinitely many prime numbers. Finally, and I promise this is the end of the monologue, there's always room for doubt just about the reasoning, even if you have no doubts about the logic or the axioms, because typically the reasoning is very involved. And you can make a mistake. Maybe you're sleep deprived. Maybe you messed up on this one. What's that?
That's what the computers are for now. Maybe we go full circle.
Maybe the computers were programmed with an error. I mean, what I'm saying is, there's this ideal that math somehow avoids, all philosophical doubt. Math is the land of certainty. Math is that thing that Descartes was searching for when he said, "What can't I doubt?" And in my view, that there is no such land. You don't have to face up to it. You don't ever have to become. You don't have to ever see how the sausage is made, and then forever, and you're stuck with philosophy and philosophical words. You don't have to do that. Maybe that's the better way to live for most people, but it's just false that there's any view that is quarantined from the philosophical debates, in my view. And so if one is trying to motivate the idea that we should seek proofs in math which at least have a formal surrogate because those certify and establish and end all questions about the validity of the argument, that strikes me as a misguided reason, because there's nothing that does that. And just the final thing I'll say, sorry I said it would be the final, but this is a PS. PS, if it occurred to you to say, no, but we can at least establish the following. The following argument is valid in a logic. The following, if classical logic is right, then it follows from the Peano axioms that there are infinitely many prime numbers, or something like that. Unfortunately, even what follows from what in a logic is background logic dependent. It's meta theory dependent. So it's turtles all the way down.
Could you explain that though, very briefly?
Yeah, I mean, it's the concrete cases are kind of technical to show, and I'd have to introduce like the easiest cases.
But
involve paradigm.
But are you referring to the inference rules, that sort of thing, in the meta theory?
Yeah. So
it's up to that.
So here's the basic point is that what follows from what is a claim that you make from some perspective where you help yourselves to certain rules of inference and not others. And the point is that what inference rules you regard as legitimate in reasoning about what follows from what in a logic will depend on the conclusion you arrive at about what follows from what in that logic. For example, if your meta theory is paraconsistent, you can have different answers to the question than if it's classical. And actually some really nice illustrations of this are in Stuart Shapiro's book, Varieties of Logic. I forget what chapter, but he has a chapter specifically on this meta theory dependence. So that was just one long diatribe saying that the second motivation and the second notion of proof I actually think turned out to be just hopeless. Like, it begins with Aristotle, The idea that, maybe proof is something where we can all agree to it without agreeing on the meanings of words, without, like, it's just something you can check by looking at the forms of strings of symbols or something. And unfortunately, I think that turned out just to be something that never could, it never transpired. Sociologically, there's a lot of agreement. But if you want something that, like, avoids all philosophical doubt in the kind of way that Descartes was looking for, and the way that we still talk often about mathematical proof, that doesn't exist in my view.
Okay, so if this second branch of the proof is not of the proof, but of reasons for having proofs, that they conclusively
Yes.
prove certain things, is a fantasy, then why rigorize the calculus? Why was that so important? But
yeah.
So again, bracketing, to use your word and your caveat, bracketing the fact that you're not a historian, though you do a pretty good job wearing the historian hat. How did well, it's easy as somebody who's not a historian, when you say things confidently, I believe you. So maybe you are just really, really butchering everything. I did a podcast with CT Win about a week ago, and we talked about how you should go about selecting experts. It's an epistemic problem. How you go about selecting experts in areas in which you're not an expert yourself, because you can't evaluate whether or not they're right on certain things. But so anyway, the calculus. Take it from here, historian Justin.
Right. Yeah. Okay. So I'm going to give this part of the lecture in Latin. No, but right. So, Newton and Leibniz, baby's first history of calculus here. Newton and Leibniz famously came up with the calculus independently of each other, and their approaches were slightly different, but both of the approaches involved something like what we today call infinitesimals, which are quantities that are smaller than any finite number, but not zero. And this is, in fact, by the way, I mean, if you're not a math major or, philosopher who's interested in this kind of stuff, this is, by the way, still how you teach calculus to, like, physics students. I mean, if you look at a typical physics book and
really?
Mathematical Methods for Physicists, those books are not rigorous about typically about the epsilon delta definition of limits and the derivative and stuff. So what you talk
about, I get the names Kiesler and Kreisel confused, but I think it's Kiesler who was a mathematical logician. Right. Well, maybe they were both mathematical logicians, but anyways, Kiesler was so taken by Abraham Robinson's non-standard analysis that he tried to turn non-standard analysis into a pedagogical tool, because he thought that infinitesimals were so much more intuitive. So he would teach. He has a textbook for beginners for calculus that is non-standard analysis based.
That's interesting.
Rather than
Haim had told me. But anyway, Haim had told me about this, about his passion for this. I didn't know he wrote a textbook. That's interesting. But so I mean, for ordinary purposes, unless you're interested in foundations or math for its own sake, it's perfectly fine to say something like, what's the derivative at a point? It's just the slope as the difference between x values goes to zero, gets arbitrarily close, and you leave it at that. What does it mean to go to zero and all that? And you just leave it at that. Or when you say that the x values are infinitely close or something like that. I mean, it's a perfectly standard thing to do. And in my experience reading physics books anyway, it's completely standard to talk that way in differential geometry and, in all sorts of mathematical fields where people aren't worried about foundations. But there are real questions about that argument. And Bishop Berkeley, who was a philosopher in what was this? I guess this was the 17th and 18th century, who, his his really, his real claim.
Yeah, George Berkeley, 1685 to 1753.
Yeah. So
But so okay, so Leibniz and Newton, even though they did it independently, they both had a very intuitive conception of the calculus that employed this notion of infinitesimals
yeah,
that wasn't rigorous.
that employed something like a notion of infinitesimals or infinitely close or going to zero or something like that without telling us what that really meant, um, and and uh, so in I can't remember the date of the pamphlet of Barclay's, but I think it was the early 18th century that he published this. Um, he
The
Yeah,
Analyst,
the
1734.
okay. So so far so good. So Barclay, whose real claim to fame has nothing to do with math. He's famous because he gave a really penetrating criticism of the early modern philosophers' distinction between primary and secondary qualities, and argued on that basis, and among other things, for what's today called idealism, which doesn't mean like everything's going to work out great. It means that everything is somehow mind dependent, or sort of the world of physical objects are actually mental entities, and all that exists is mental entities. It's opposite of course, the idea that everything is physical, and that even
Which seems to be experiencing a revival these days,
did you say
at least in Columbia's philosophy department and with applicants.
idealism?
Yeah, well, it seems like so many people are writing on German idealism these
Oh,
days.
okay,
Yeah.
right, yeah. So that's possible, yeah. Well, so anyway, so that's his claim to fame. I mean, he was a philosopher, he was a theologian. He wasn't a mathematician, though. He did some work in the sciences, and was taken very seriously. His critique was taken very seriously, and and what he did was sort of make this kind of satirical pamphlet. And the point of the pamphlet was not sort of why we still read it today, but the point of the pamphlet was he was, again, a philosopher and a theologian, a believing theologian. And, the scientific revolution had taken off. And this was the era where, there started to emerge a culture among scientifically minded thinkers that somehow um, you know real knowledge is founded on, if not observation and experiment, because some of these people were what we today call rationalists, at least something like mathematical science or something like that. And meanwhile, debates about theology are just kind of like how many angels can dance on the head of a pin, and there's no way to confirm them or refute them, and they're often incoherent and all these things. And Berkeley, who was a believing theologian but also a very smart guy, made a very funny pamphlet, basically arguing that if you think debates about God, for example, are incoherent, or sort of the the logical like what's the word? Sort of aren't sufficiently careful logically or something. Let's look closely at what grounds your whole physical science. Those of you who are making this criticism, which wasn't Newton, by the way, who was a believer in God. He was a very seriously theological character, but and neither was Leibniz. But people sort of on behalf of the Newtonian physics were saying this, and so he just submitted the kind of reasoning that does show up very explicitly in Newton's work and Leibniz's work to critical scrutiny, and he made a perfectly legitimate point. I mean, the way that one normally presents these kinds of arguments is that you figure out the slope. So to compute the derivative at a point, you figure out the slope by letting the difference between the value of f at x and the value of f at x plus dx be very small, but not zero, because if it were zero, you'd end up dividing by zero.
Right. Which is undefined.
So you let it be very small, and you then compute the slope, but then you let the difference go to zero or be zero at the end, because you want to know the exact slope at the point. And if you were to let the distance be finite between x and x, x plus dx, you wouldn't get that. You just get another slope. You'd get a secant line. So we've just submitted very carefully, and he said, "Look, is dx zero?" It wasn't called dx. I think it was O in Newton's work. He had this term.
The fluxion.
What? Yeah.
Newton
went through phases, but one of his phases involved the notion of a fluxion, and I think that the term he used for this difference was O, and Berkeley just asked the reasonable question: look, is O zero or not? You can't change the meaning of O in the middle of an argument. That's what's called an equivocation. An argument can't be valid if it means one thing in the premise and something else in the conclusion. So is O zero or not? You can have it either way. The problem is neither way gives you the result you want. If it's zero, then you're dividing by zero and the thing doesn't make any sense. If it's not zero, then you don't get the tangent, you get a secant. You don't get the actual slope at a point. So this was just like a very good point. And by the way, many calculus books still to this day sort of begin by we had this idea of the calculus, and then Berkeley pointed out, like, this really doesn't make a lot of sense. And so then people like Cauchy and Weierstrass and Bolzano, who's also
the ghost of a departed quantity.
Yes, exactly. He called them I think the pamphlet finishes with, like, what could these be but the ghost of the departed quantities, these fluxions or these. Look, in my view, his point was totally good, and I think this is the standard view of both historians and mathematicians. And it wasn't until the 19th century that it was really remedied in terms of the epsilon delta definition of the limit. And this is an example of something that periodically happens in the history of math. People who sort of he was kind of making a cheat. The pamphlet is actually very funny. So he was sort of chiding these scientific mechanists who like to make fun of theologians, but the substantive point was very serious, and this is something that happens periodically. People who call them philosophers, call them sticklers, it doesn't matter. They worry about the foundations. And of course, most people don't care about the foundations. I just said, still to this day, most physics books don't get into the epsilon delta definition of the limit. So you can sort of get by for a long time without worrying about foundations. But it ends up mattering for a systematic edifice. It matters for systematic theory. And so you have people like, Berkeley, you have people like Russell, who came up with Russell's paradox, who come up with these issues that seem peripheral to any mainstream concern. So take Russell's paradox. Russell said, under what conditions can you collect sets? Because set theory had taken on a foundational role at the turn of the 20th century. And it became what was seen as like maybe the clearest concept we have, and we should build math out of set theory. And under what conditions can you collect sets? And here's the obvious thought. Whenever you have a predicate, like a well-formed predicate, if you have a condition, take the things that satisfy it. And if the condition is like something like being not self-identical, no problem. In that case, the set is the empty set. And that's exactly what Frege thought in his famous attempt to found math on logic, in his sense. And Russell said, but that can't be right, because consider the predicate of not containing yourself. And now consider the set of all sets that don't contain themselves. Does it contain itself or not? And if it does, it doesn't. And if it doesn't, then it does. So something needs to give. And most people would say, oh, come on, who cares about that weird, contrived predicate? But if you don't know when you can form something that's like a well-formed, if you don't know when something will give you a set in general, you don't know if you're going to end up running into contradiction in a totally ordinary situation. And this is why people like Hilbert took these kinds of paradoxes so seriously. And this is why we ended up, eventually arriving at what somebody might call a pretty gerrymandered set of axioms, because at least they look like they won't give you inconsistency. But that's another type of Berkeley case. I mean, Russell wasn't primarily a mathematician. He's a philosopher who wrote something like about 100 books on marriage and the mind-body problem. And he wrote the Einstein-Russell manifesto about nuclear war or nuclear arms and so on. But that problem trickles down and has immense implications for what math becomes, what's regarded as the standard of rigor, what are taken to be the basic principles. And I think that's very much what happened with the Berkeley case. Berkeley wasn't a mathematician, but he had a point. And I think anyone who studies it carefully, has got to grant him the point. And it turned out not to be trivial to respond to that point. So that's the cartoon history from the non-historian.
So he had a point. There were serious problems conceptually with the calculus as developed by Newton and Leibniz. But then I go back to your distinction between the two roles for proof,
right,
and then the role of rigor. And if providing this foundation for the calculus doesn't conclusively settle the question
right,
of whether or not we have a legitimate system before us, why do it at all? Was there a good reason to rigorize the calculus?
So here I think the answer to this is just what we say on the first day of epistemology class, when often people, the first thing that's assigned is Descartes, and he thought about what he can't doubt, what he can be certain of. And most people agree that, if you don't invoke God in a circular way, you really can't be certain of anything. He probably is even wrong that he can be certain that there is thinking or I exist or something like that. But it's to throw the baby out with the bathwater, whatever, to say, therefore I can't know anything. Knowledge doesn't require certainty, and it's not an either-or proposition. And just because the ideal of somehow certifying proofs in this just beyond all doubt kind of way is, it seems to me, a fiction. That doesn't mean that some things aren't way more better supported than others. I mean, it's like, here's two propositions. The number of stars is even, and there was a computer before me. And I think those are on quite different footing. And so it certainly makes sense to try to increase your rational confidence in any theory you want to develop, and to try to establish as much evidence as you can for it. And if, for example, the foundations of the theory just blatantly involve a equivocation or are explicitly contradictory, that's bad news, and you should try to resolve that. But that doesn't mean that the result of the exercise is certain. It just means it's on a much better footing than the original. So I'm not against rigor or something. I just don't think it gives you what sometimes, I wouldn't even want to say sometimes, very often it's advertised to give you. It doesn't give you certainty. It doesn't give you, something that there could be no reasonable suspicion of or anything like that. But it might well give you very good reason to believe. In fact, I think that's the case.
I also see a little bit of a parallel between Eudoxus's proportions and our real numbers, in that I wonder whether it's really fair to say that what Cauchy and Weierstrass did was really providing a foundation for Newton's and Leibniz's calculus, because there's no there are no infinitesimals there, whereas
Right.
there are infinitesimals in Abraham Robinson's, which came
Right.
like 70 or 80 years later, where they're the reciprocal of hyperintegers.
Right. I mean, this is it seems to me one of the liabilities of the kind of view that I think you attributed to Heim, that we never give up mathematical posits in the way that we gave up the ether or the planet Vulcan or something. Math, it seems to me, is largely about reinterpreting old language in new terms. So it's not anyway. It's really hard to make the case, for example, that we've just learned a whole lot more about the numbers of the Greeks. The numbers of the Greeks were expressed with lines, and irrational numbers was a contradiction in terms. So what's true is we can reinterpret what they did as claims about numbers in our sense. But you don't want to trivialize the thesis that math is cumulative and we never throw anything out, because, of course, if you ever have a consistent theory, I mean, here's a basic meta theory of first-order logic. If you ever have a consistent theory, you can always make it come out true by reinterpreting it. That's just to say that every consistent theory has a model, which is what's known as the completeness theorem. So if you're allowed to just reinterpret any theory, physical, ethical, philosophical, and it's not just overtly contradictory in the formal sense, you can make it come out true. Now, it might be there might be something deep about the fact that that's all we seem to care about in the math case. We don't seem to care about what it's sort of really about. But that sort of is comparing apples to oranges at this point when you say, is math like physics? Are there revolutions, or do we just learn more about the same thing? Kuhn worried that the notion of mass changed between Newtonian and relativistic mechanics. So we didn't learn more about mass. And most people say, oh, give me a break, that's an overstatement stuff. But the hypothesis about math would be that nothing like that has transpired. We just learned more about the same old objects. Sometimes we added objects, but we never threw them out. But if you're so wildly reinterpreting things through successive revolutions, not to mention changes of standards of rigor and method and so forth, not to mention changes in priorities, like what counts as an interesting question, like doubling the square using, doubling the cube using compass and straight edge or something. I mean, with these certain restrictions on you, those are not the kinds of questions people care about today. So there's so many ways in which math, like everything else, as far as I know, has changed. You don't want the thesis that it's somehow special and cumulative to be trivial just because you can always reinterpret what people did in the past so that it comes out true today in your language. I mean, sure, that's fair, but you could do that anywhere.
So what then is really the alternative way to answering the question, what is mathematics, if you aren't just going to point to sociological facts or historical facts?
Yeah, I mean, it's not that I think that that's the wrong approach to the question. It's that I think the question, if really seen as a factual question, is a misconceived question. I mean, I don't think there's some deep essence to math. I think that math is, like most things, different moments in what we call math bear family resemblance to each other. And it's a kind of practical question whether to categorize them all as the same or different. I mean, whether to call what the Egyptians were doing the same thing as what, contemporary algebraic geometers do, strikes me as just, there's no deep answer to that. It's how you want to categorize. There's dramatic differences between what they were doing. Totally different priorities, totally different methods, totally different concepts. Is it the same? I don't think that that's like the question of whether there are gravitons, I don't think that. So my own view, roughly speaking, even though I just co-taught a class with the title "What is Math?" is that question is misconceived if it's really a factual question. And the right thing to do in place of ask that question is just to explore similarities and differences between what we call math in a, say, history of math book today versus in the past, across cultures, across even decades in the 20th century and the 21st century. And it's interesting and telling, I think, to speculate about what it's going to be using the ordinary vocabulary, with the increasing role of AI and machines to both assist mathematicians in proving theorems and to actually discover proofs of theorems. And so that's my I don't think that there's a better way to answer the factual question, what is math, than just something like analyze the concept of math. But I don't think you should analyze the concept of math. I think that you should set that question aside and just explore similarities and differences between traditions that typically are called mathematical.
So I'm sympathetic to Heim in the sense, at least, that I want to find something unifying about all of mathematics. But the biggest problem I have with this account, or it could just be with his way of putting it, and I've raised this with him before, is that it just seems to, or he at least, it doesn't want to give answers or ways of answering certain questions that are still very important to us, like what mathematical objects are. I mean, that's something people have been talking about for 2,000 years, and I think it's an important question, even if the answer is there are none. But or how we know about mathematics, and these are questions that you don't get. Well, maybe you could say, oh, we know about mathematics because we read a textbook, but that doesn't really answer the interesting philosophical question. So how do you go about answering those sorts of questions if you're not going to be using the history, sociology, practice route?
Oh, well, there I think you just clarify what your target is. And in fact, Michael Harris, our colleague Michael Harris, in a discussion I had with him, or have had with him a couple of discussions, where he talks about the philosopher's math versus, the mathematician's math versus the man on the street's math, or whatever. And I mean, his point is that one's concept of math, it does seem really depends on who you are. A contemporary algebraic topologist's concept of math is not the logician's concept of math generally, which is not the not the actuary, the actuary's concept of math, and so on. So what you can ask is concrete questions like, how do we know, if we do, the axioms of first order Zermelo-Fraenkel set theory? How do we know that a classically valid proof is classically valid? How do we know that classical logic is the right logic? That's not going to be, though, like, it would be false advertising to say that's the question of how we know math, because there's so many different things that are math, most of which are not how we know ZFC or things that follow from ZFC in a formal system. So that's kind of the question, how do we know philosopher's math, to use Michael Harris's terminology? That's the kind of question. But then I think you can ask, also questions, how do we know math in the much more ordinary sense of math, that, like, where the Egyptians were, making use of something that we might today, in a different context, characterize as empirical science for purposes of agriculture. How do you know that? And you can ask that question. How do you know? How do contemporary number theorists working on the Langlands program, know the theorems that they establish by basically introducing, super loaded concepts that it takes forever just to understand what the concepts are? and they don't use formal proofs. They probably haven't, many of them, I bet, haven't taken a class in logic or would even be able to tell you what a Hilbert system for proof system is, much less worry about the axioms of Zeus. How do you know that? How do they know? So there's just lots of different questions, and I think part of the answer is, as always, going to involve psychology and our best science of the brain and the mind, but that's not going to settle anything normative about sort of when your belief is justified. And so part of the answer is also going to involve basically questions of policy, intellectual policy, and discussions of, what makes a certain kind of intellectual state reasonable. And how does that differ from the state, for example, I'm in with respect to the proposition that the number of stars is even, where it would be unreasonable for me to take a stand on that question.
So do you find, and this is a big question, that the Benacerraf-Field problem has been sort of answered to your satisfaction?
I wouldn't want to say that. What I'd say is that I think a lot of progress has been made on it, and
well, you just recently wrote a book on it, right? Or
a
mini book.
It wasn't just on that, but right, I wrote a book on mathematical knowledge and what I call pluralism about math and its relevance to philosophical areas more generally. And
could you say what the problem is?
Yeah, sure.
And
so
whether it's still problematic for you?
Yeah. So look, I think that there's a lot of distracting ways to put the problem. And I want to be careful not to do those. But let me just advertise what those are. Some of those where I think you really just miss the point, and you end up you might end up dismissing the problem as silly because you don't understand what the real issue is. So here's an example of a silly way to put the problem. Math is about Platonic objects, and how could we ever know anything about Platonic objects? They're not things with mass energy or quantum number and so on. What kind of physical interactions could our nervous systems have with them? And, somebody's going to respond to that by saying, well, then I don't think math is about Platonic objects. So that's not the useful way to put the point. The useful way to put the point is, here's just the following correlation that anyone who's non-skeptical about math accepts. In general, if the mathematical community claims to prove that P. And here's something else, though, that people tend to accept. Whether P is true for a typical mathematical theorem, like let's stick with Euclid's theorem because it's simple. There are infinitely many prime numbers, okay? Whether that's the case doesn't seem to be up to us. We don't seem to get to make it the case that there are or aren't. We can change our conventions and mean different things by the same words, but that won't change the thing that we actually say presently with there are infinitely many prime numbers. So, okay, you got two things. You got the fact that there's infinitely many prime numbers. You got P. I'm not reifying fact here. I'm just using that as another. Here's two things. There are infinitely many prime numbers. Here's another thing. Mathematicians and people actually who have taken basic math think there are infinitely many prime numbers. Question: what explains that correlation? And that question is a good question. I mean, in the physical case, like here's another fact. Things accelerate down to the Earth at 9.8 meters per second squared. Here's another fact. People believe that things accelerate down to the Earth at 9.8 meters per second squared. Okay, why is that? I mean, here's the basic answer to that question. Because they do. And things deflect photons that hit our retinas and stimulate our optic nerves and so forth. Our nervous systems are affected by the actual fact. Okay, is anything like that kind of story, however you think of mathematical reality, maybe it doesn't involve any objects at all, like logic is often thought to involve no objects at all. Is anything like that story going to explain the correlation? It doesn't seem like it. I mean, it's incredible how little progress has been made, for example, in the sciences explaining the correlation as opposed to how we came to have the beliefs we have. Cognitive science and evolutionary psychology and so on are bearing on the question of how it is that we come to have for example, numerical concepts, how we estimate the size of collections of things in our environments reliably. Okay, but they're saying almost nothing about, I'm not asking how you have the beliefs you have. How is it that you get that they tend to be right? And not about things in our environments, but things like about prime numbers and infinitely many of them. So there's different things you can say. One thing you could say is, well, you know what, now that I think about it, I don't actually want to say that there are infinitely many prime numbers. Okay, but that's a little tricky because you're up to your ears in statements like that in any regimented physical theory. I mean, what could it mean to say I believe the Lagrangian density, the standard model, and I believe the field equations of general relativity, and eventually somebody's going to come up with a theory of dark matter and energy. I believe all those things, which is just going to be a bunch of math, basically. But I don't really believe in math. Don't get me wrong. Okay, if you want to say that, as Quine famously put it, you got to put your money where your mouth is, and that's what somebody like Hartree-Field tries to do. And in my view, unfortunately, that's not going to work out for reasons we can talk about. But he at least honestly tried to take on the question and didn't just sort of talk out two sides of his mouth, by saying I don't believe in math and I'm not a Platonist. You're just calling me a Platonist. And, if you want to say math is like mind dependent, and you don't want to say the field equation, the facts about gravity and the space-time curvature are mind dependent, then you need to figure out how to say stuff about space-time curvature that's true that doesn't involve the math. So it's a little bit okay. So the Benacerraf problem is basically just to explain that correlation. And I think we have made progress on explaining that correlation, but I don't think the problem is done. In the original formulation of the problem, Benacerraf sort of conflated two issues, but in a way he was right to conflate them because they're both issues that have to be resolved. The one issue is semantic. How do words get to mean what they do? How do we get to mean finite, for example, by finite when we know that that's not a first-order definable concept? And the other issue is, assuming the determinacy of our language, how do we get to have reliably true beliefs about whatever we're talking about? Where, again, about can make it sound like I mean they're Platonic. No, I don't mean anything like that. It doesn't need to be about anything in the sense of extra ontology. I just mean that, how does it get to be the case that when I think there are infinite many prime numbers, there are infinite many prime numbers, even if that doesn't really
and the problem is getting both legs to cohere, right? Because there are theories that do one fine, theories that do the other fine, but the Holy Grail is one that gets them both.
Well, sort of. That's how Benacerraf thought of it. Benacerraf thought that the way to put the problem is that there's a tension between giving a plausible semantics for mathematical language versus giving a plausible epistemology. But what he meant by plausible semantics was not something that necessarily resolved the determinacy problem that I just mentioned. He just meant like you should be able to give truth conditions of mathematical sentences that cohere with the truth conditions of other sentences of the same surface form. So, for example, there are infinitely many prime numbers should have the same truth conditions or analogous truth conditions as like there are infinitely many stars. There should be some stuff, and it needs to satisfy the predicate, being a star or being a number. And his thought there, Benacerraf was kind of working with the Platonic thing, because his thought there was, so there's got to be these Platonic entities, and how would you? But Hartree-Field, in his book Realism, Mathematics, and Modality, I think nicely separated out just the epistemological point, though he has a discussion of the semantic point. And I think he does a better job illustrating why it's kind of distracting to put the two problems together, and also to think that the epistemological problem has much to do with whether or not the semantics is a face value semantics that mirrors the semantics of the rest of language. So I won't go on, but just to say that there are accounts advocated by Charles Chihara and Jeffrey Hellman where math isn't about anything special. It's basically complicated. In the Hellman case, it's basically complicated modal statements. And I think where the modal it is possible and it is necessary. And and the modal operator there is taken as a primitive, not analyzed in terms of possible worlds. And I think Field is right to say, okay, but now the question is just how do you know those modal statements? What's the correlation between your judgment that the modal statement holds and the modal fact, where the fact, again, is not an extra thing, but just something I could say. So I think that the literature and the problem, we've gotten clearer on what it is, and it's not, I think, quite what Benacerraf formulated.
Okay. That was all very helpful, because I think I'm working on a literature review on this, so that was a great primer. I'm going to take us in a slightly different direction, though.
Okay.
We'll get back to the calculus. But I'd really like to talk about Zeno's paradoxes, particularly because I find them so compelling. And I think they're some of the first problems that got me interested in philosophy to begin with. So maybe, well, there's the Achilles and the tortoise, and then there's the dichotomy, which I talked to Nick Huggett a bit about it, and I guess just means cutting in half or cutting in two. Interestingly, do you know the etymology of paradox?
No.
Okay. It means, well, I'm probably going to get the Greek wrong, but para and doxa is against belief. So we're taking premises that we believe, and then the conclusion that comes from it is goes against our beliefs. But so do you just want to start with the dichotomy as opposed to the Achilles and the tortoise, since they kind of reduce to the dichotomy?
The Achilles and the tortoise adds anything really to two different versions of, I think, what you mean by the dichotomy. So the basic, I mean, here's two different versions. Suppose I want to go some unit of length, like a foot or something. Seems like I can do it, Seems like I can move. Okay, to go that unit of length, I need to go half the unit of length. And to go, and then I need to go half plus half the half. And then I need to go half plus half the half plus half of the remaining, and so on. That's one version. In a way, the more I don't want to say it's more interesting. The more striking initially version is to say the same thing except
the regressive form.
Yeah, is to say the same thing except do it the other way. So suppose I go unit of length, I need to go half to do that first. So that's logically prior to going the full length. To go half, I need to go half of that. And to get blah, blah, blah. Well, that sequence doesn't even have a first member. So there's an issue about even what, okay, so here's the big picture. The big picture is Zeno saying, okay, wait, so to go any finite length, doesn't matter how long, I need to go an infinite sum of finite lengths, because any one of those halves is a finite sum. And it goes on forever. There's never a last one. So, on one reading, what he's saying is surely an infinite sum of finite quantities cannot itself be finite. And you can't go an infinite distance. Now, Aristotle responded, but you can go an infinite distance because time has the same structure, and so you have an infinite sum of finite sums to go the distance, so there's no problem. The right response to that is that just doubles the problem, because now how do I manage to traverse that time? So in addition, in the regressive formulation, there's an issue about how do I even get started? Because there's no there's no sort of first step. That's the wrong way to think about it, of course. So that was Zeno's paradox, and you said we'll get back to the calculus. I mean, the typical calculus student, among other things, they learn about Berkeley maybe. If they hear some history, they also learn about Zeno's paradoxes, and almost always in that little paragraph or first section or something, it'll say something like, and that problem wasn't even solved until the calculus. But I think it's a good question whether it was solved, if there's a problem at all.
So the progressive and the regressive form raise slightly different questions. But the progressive one, at least, I mean, the intuition is that we can't complete an infinite amount of tasks in a finite amount of time. Is that
I don't think I would. I wouldn't want to put it in terms of tasks, because that invites the question of, oh, you're individuating tasks in the wrong way. I mean, there's only one
okay?
task or something.
Oh, yeah. Well, I think of it. I think of each like sub interval you have to go through as a task. You don't really. You just don't like to phrase it that way.
So I think Heim would, one of his complaints about Zeno's paradox is that he's sort of loading the dice, because he makes it sound like, because you can chop the interval up in infinitely many pieces, there's like infinitely many things you need to do. And I think that, that's not where the action is. There's an infinite sum of distances that are each finite that you need to cross. That's true whether or not you have one task or infinitely many tasks.
I feel like you're the one making this like a verbal issue.
Oh, okay.
Because to me, I think I don't see it as problematic to say to think of each interval as a task if we want to use that language.
That's totally fine with me. It's just that I don't want to be vulnerable to the criticism. Oh, but that's the philosopher's way of talking about tasks. There's only one task, and it's to move your foot one step or something.
Okay. So with that aside, then, is the main intuition that we're working against in the progressive form is that you have to move an infinite amount of distances or subintervals in a finite amount of time.
Finite distances, I think, is the key point.
Yeah, finite distances.
Mm-hmm.
And does it raise any other prima facie questions, like right off the bat for you, or?
Well, I mean, as you say, since it's a paradox, that is, since the conclusion is supposed to be unbelievable, that we can't move, I mean, an immediate question is like, what's the culprit? And, we have been raised in the post-calculus era, where people think that the culprit was exactly the assumption that an infinite sum of finite quantities itself can't be finite, because we would say that yes, it can if the series converges. But to foreshadow, I think that is an equivocation with the word sum, because an infinite series is not literally a sum. It's for example, depends on the order that sometimes that you put the quantities in. It's not literally a sum; it's a limit. And but anyway, but something else that you might think is the root of the problem is infinity, right? So another worry that you might think immediately this suggests is that, oh, there's something messed up with the notion of infinity. The result is obviously nuts. So something went wrong. Maybe what went wrong is precisely the idea that it makes any sense to infinitely divide space or time. I should say, to his credit, Zeno considered this possibility, and he has another paradox, which is supposed to apply to the assumption that that space is discrete, not infinitely divisible.
Yeah, well, I want to get to that
Sure.
in a minute.
Sure.
But so you don't find the calculus solution compelling? Well, could you maybe first say how? I mean, maybe how we're supposed to imagine or understand the way the calculus is working on a physical level, because when you just see the numbers, it's all very abstract and it doesn't seem to just answer. But how do you do it? How does Achilles get the 1 foot or whatever he has to do?
Yeah, no, I think that's a reasonable question. And of course, there were some great debates. Actually, speaking of Benacerraf is one of the contributors to these debates. There were some great discussions in the mid-20th century. Though the philosopher, I can't think of his first name, but his last name is Thompson, I think, is the one who is generally considered the most sort of penetrating critic.
I'll find his name.
who basically thought Zeno was right, and the issue was infinity and what are called super tasks. That is, tasks that would involve some infinite process. And he had this great example of, like,
The lamp.
yeah, imagine a lamp that, at half a second you turn it on, at half plus a fourth you turn it off, and so on forever. After a unit of time, is it on or off? And this series, of course, doesn't converge. But if infinite processes make sense, it seems like there should be a fact of the matter about what the state of the lamp after that sequence of events. Now, you have to idealize in certain ways, because, for example, if, like, literally you're imagining, like, switching a switch and the switch is the same length, well, then you need the distance to get smaller and smaller as the time goes on too. And eventually you'll get to the atomic scale. And I mean, you can worry about things, but basically there are super tasks you can come up with that seem paradoxical and don't admit of this kind of resolution, if you think it's a resolution, because the series isn't, as it is in the Zeno case, a geometric series which converges. And so yeah, I think that these kinds of questions, look, here's the bigger question. This is another sort of aspect of just the division of cognitive labor, and a result of it that's bad. Physicists, even more than mathematicians, are not worried about the foundations of math. They're not worried about sort of the philosophical coherence of the basic principles and so on. Now, some mathematicians are, some physicists are, but as a population generally, they're not. And so you take a course in mathematical methods for physicists or something, and you learn the calculus, and as I said before, not even the calculus as we know it today. You learn a sort of fudged version of the calculus generally. And, you learn linear algebra, some group theory. I'm not sure what's totally standard for a class of that sort. Fourier transformations. Anyway, and then you just get to work using it to compute things, and that toolkit is up to its ears in commitments, like that space is continuous, that that super tasks do make sense, and it's easy to build the representational apparatus that you bring to the table and that you just inherited as a toolkit to speculations about the thing you're using it to represent. So, for example, I don't think anyone should take too seriously the fact that, for example, space-time is continuous in say, general relativity. I don't think anyone should take that very seriously as a physical hypothesis or something. I mean, it's that nobody has come up with a very good way to do general relativity with discrete space-time, and the problem of discrete space-time is closely connected with the problem of quantum gravity, and that's a very difficult technical problem. But the point is, you need to be clear about what you're bringing to the table as your tools and reading in to the data from the data, and that's a very hard thing to do when the data is often itself highly mathematical. So I think there's concrete cases of this, which I'd love to talk about, but we don't need to. But where it's just really a case of, like, if you knew some philosophy, or if you knew some logic, or if you knew this, and vice versa. I mean, the philosophers also will make confusions, and the logicians will make confusions just because they don't know the relevant physics. This is where I think prime case where discussions among specialists of different kinds would really help, just facilitate clarity. So the Zeno's paradox things, I think that there do remain legitimate doubts about, should we really believe that at the fundamental level, space-time is not just infinitely divisible, but say, for example, continuous, and that super tasks are real things, and so forth. I think those are all totally legitimate questions, even though they're 2,500 years old.
Yeah, agreed. But before we get back to that, I'm going to take you up on your offer of loving to talk about some concrete cases
Sure,
of
yeah.
confusion that would be ameliorated if the physicists knew some logic
Yeah.
or foundations or something like that.
Yeah, so I don't, this is not meant at all.
Well, let me add a caveat this time. If you have one that's particularly simple that somebody who doesn't know a ton of physics, like myself, could follow.
Well, I think you can follow this without knowing tons of physics. I mean, it involves some technical math, logic concepts, but no. Here's a concrete case, and this is nobody's fault. I'm not in any way trying to criticize physicists or something. We need division of labor, or we'd never learn anything because there's just too much. But I think we also need periods where we try to compare notes on different issues. So here's a concrete example. Okay, so here is supposed to be an open physical hypothesis, and in fact, I know many physicists who think that it's probably true or see no reason to think it's false. The universe is finite. There are only finitely many things. That certainly seems to be a possibility. If space-time is discrete, for example, then shouldn't it possibly be the case that there are finitely many things? Okay. So you can have theories then with finite models, physical theories with that admitted finite models of the universe. And, I take it that you would want that in theorizing about quantum gravity, for example, that at least your theory allows for the possibility that the universe is finite. Okay, now here's an uncomfortable fact. And this is just a fact about in the foundations of math and philosophy of math. Every theory, as far as we know, needs a meta theory. Why would you need a meta theory is the theory of the theory. Like, for example, it tells you what the theory can and can't prove and things like that. Why would you need that? Well, you need that at least to be able to say, for example, what the theory predicts. If the theory predicts something, if the theory implies something, then it predicts that thing. If it doesn't imply it, then it doesn't predict it in general, if it's sufficiently formalized. Okay, well, the meta theory of any theory, even a theory that admits of finite models, is bi-interpretable, mutually interpretable with just arithmetic. Because the theory is the theory of what's called the strings of symbols. Okay.
Yep.
Arithmetic has only infinite models. So here is an uncomfortable fact about that. It seems to me people working in foundations of like quantum gravity who really are concerned with, say, the cardinality of the universe and whether it's infinite and stuff should care about. Absent what's known as an ultra-finitistic surrogate for arithmetic, which no one has managed to even coherently say what that would be. Ultra-finitistic surrogate for arithmetic would, for example, avoid recursive and inductive definitions.
Right.
So I mentioned Edward Nelson, who is associated with finitism. He does not do that. He uses Robinson arithmetic as his base theory. So the attitude is kind of like, don't take it too seriously. No one has done what I'm suggesting would need to be done, as far as I know. So either you come up with an ultra-finitistic surrogate for the theory of arithmetic, which serves as your meta theory, or you contradict yourself at the meta level when you say the universe might be finite. Because it's got to be infinite, because my meta theory about what the theory implies and so forth only has infinite models. This seems to me like a very just clear, clean problem to come up with an ultra-finitistic theory of arithmetic, which is not a problem that should just be of interest to the 3 people in the world who care, who are skeptical of induction or something in piano arithmetic. It's a problem that we should care about trying to come up with a unified worldview. You cannot.
So why?
Go ahead.
Oh, sorry. Why can't this hypothetical physicist just be sort of an instrumentalist about the infinite in the meta theory?
Well, so first of all, it's not the infinite, remember? It's so
Well, it's arithmetic.
right, which the model theory of it postulates an infinite set, but the theory itself just says that for any number there's a greater one. For example, every natural number has a
Okay.
successor. So I don't know what you could mean to say that you can be an instrument. Let's take concrete case again. Okay, here's something. Let's suppose I have some physical theory that admits of finite models. I formalize it so it's clear what the theory implies and doesn't imply. Here's a claim about the theory. It implies a contradiction. Okay, if the theory actually doesn't imply a contradiction, that claim is consistent. That's if the theory interprets arithmetic. Sorry, if the original theory interprets arithmetic, and you would presumably need it to do any interesting physics. That is true only in a model where there's a number after all the finite numbers. It's an infeasibly large number because it's an infinite number. So a model of this, witnessing this consistent but presumably false possibility, is a model with not just arbitrarily large finite numbers, but a number after all of them. So if you want to say something like, I take an instrumentalist attitude towards the, say, infeasibly large natural numbers, I don't know how you can say reasonable things about, for example, there is no natural number. The codes of proof of 0 equals 1. That you need to say no number is such a number. Like if you want to say the theory is consistent, what does that mean? It means among all the numbers, none of them codes a proof of 0 equals 1. You don't just want it to be that none of, say, the numbers that correspond to sizes that are instanced in the universe codes because maybe if there were one more thing, that would code a proof of 0 equals 1 or something. So I don't know how to get rid of talk of arbitrarily large numbers. Now it's true that when I said that at the meta level you need the theory has only infinite models, I was then talking from the model theoretic perspective, and that's not the perspective of the theory, which is the theory. It talks about all the numbers, but it doesn't talk about models of them. That's another level of infinite commitment. It's a commitment not just to arbitrarily large numbers, but to being able to collect them, and then you could maybe take the power set, for example. But I don't see how you can get rid of talking about arbitrarily large finite numbers if we think of metalogic in the way that we do to this day.
Okay, no, sure, that makes more sense, but I'll also have to listen to it again to make it make complete sense. So back then to the dichotomy paradox. I mean, my intuitive, uninformed physical response, physically uninformed response, is that, okay, well, I really just want to get rid of that assumption that we can just continually cut that interval in half and create an infinite amount of sub-intervals, and consequently then accept an atomistic conception of space. But I understand that has physical problems in the sense that they, like you said, people haven't figured out how to do general relativity with discrete space-time, though
that's not quite
string theorists.
Yeah, right.
That's not quite what you said?
Well, no. So the specific difficulty is coming up with quantum general relativity, quantizing general relativity, which requires more. You need to be able to, for example, think of that the state of the space-time is in a superposition, for example. I mean, that would be part of the difficulty. So you need to be able to apply the note, assuming that your approach is to apply quantum mechanics to gravity rather than to somehow, that's the normal approach, to think that there are gravitons. It's fundamentally a quantum theory. one of the problems there is that, okay, so all of the obscurity surrounding quantum mechanics then needs to be able to make sense as applied to space-time. Like space-time can be in superpositions, for example.
Well, maybe at the quantum level, we are willing to bite the bullet and accept that things aren't going to behave intuitively. But my understanding is that Zeno foresaw this sort of objection and came up with, or this sort of response, and that we reject the continuity of space and posit discrete space. And he had another paradox that posed problems for this as well.
Right.
And what was that one called?
I think it's called the stadium paradox. Yeah.
Yes, the stadium. Can you explain the stadium? And I am going to put up a picture when I do the editing.
Okay, so I should just warn you first of all that I'm going to have to go in about 5 minutes. I'm sorry.
Okay.
But
no, that's no problem. Wait. Okay. Then don't answer that question. Since I have 5 minutes, I'm going to ask you. Okay, last question. Yeah. Ronnie had another question for me to ask you. She said, you used to be really into Indian metaphysics.
Yeah.
And that it shaped your current views. And I don't know Indian metaphysics, or furthermore, I don't know what Indian metaphysics she could be referring to.
Mm-hmm.
So what is she referring to, and how does it affect your current views?
Oh, well, yeah. So no, this is this is just kind of autobiography. So my first love philosophically, was basically Indian philosophy, and then I was more interested generally in what's today called Buddhist philosophy. I had not even read any what's called Western philosophy yet, so I took a zillion courses on all that stuff. But that was my first year of college, and I went to a really small college where there was only one person associated with a given thing, and often no people. And so there was one person, and I took all the classes he offered. But that was all I could do with Indian philosophy. And so when I applied to grad school, I felt very torn. I love Indian philosophy and Buddhist philosophy. But at the time, things have really changed. Now I can speak from being on hiring committees. At the time, there literally was just, first of all, it would be just about impossible to get a job in a philosophy department. Second of all, there was just really nowhere to go. The University of Texas Austin had one person doing Indian philosophy, and that was the only person that I knew of at a graduate program, except for a program you could pay for in England at the University of Liverpool that had just been founded, a master's program, and I couldn't pay for it. So the thing that tugged at my heart was, do I go to NYU, which is great for philosophy generally, but it didn't have anyone doing non-Western philosophy. I think maybe it does have people doing that stuff now, but it didn't at the time. And again, now this is sort of, people are realizing we should do this more, but at the time it was just really, it was much worse than saying I do Hegel or something. It was
that's good in some places.
Yeah, right. I know. Or do I go to Texas Austin, work with basically one person, learn Sanskrit and so on? And I decided, what I decided, and thankfully now I have tenure. So one of my long-term hobbies is going to be to dig into that stuff again. But no, I think that
awesome.
I'm no expert. My interest is amateur because I have not, gone beyond what I learned as an undergrad my first year. But I've tried to keep up somewhat on it, and I'm really glad we hired someone who does it. And there's a sense in which I agree with my understanding of at least the Madhyamaka metaphysics of Nagarjuna to a considerable extent. I also there are also sort of more general features of Indian philosophy that I prefer to Greek philosophy and to Western philosophy in its priorities, kind of what it regards as interesting questions. I think that it speaks to me more. So I'm very glad that that stuff is making its way into contemporary discussions in a way that it definitely wasn't when I was, applying to grad school.
So okay, we sort of got like cut off towards the end, so I didn't get to hear your full response,
Okay.
but that's okay because it's still recorded, so I'll be able to hear it afterward. But anyway, thanks again, Justin. This one was totally awesome.
Yeah, no, thanks so much for having me.